Hello, everyone, and welcome to our opening webinar for the Southeast Asia Community of Practice sessions that we're going to hold. It's my pleasure to be with you tonight, this morning, maybe very early in the morning for a few of our participants who are coming from Europe. Thank you for joining. My name is Josh Novacek. I'm from the National Renewable Energy Lab here in Colorado in the United States. Today I'll be operating as the master of ceremonies. I'll be introducing speakers and facilitating questions. It's a pleasure to be here with everyone today. Today our webinar is focusing on the tools and methods to monitor system inertia. This is a growing concern for system operators that are seeing larger amounts of inverter-based resources added to their system. Traditionally, this wasn't something that the system operators really were concerned about, since there was plenty of spinning mass on the system. A variety of system operators throughout the world have introduced methods to be able to better understand their real-time system inertia and understand if they have to make changes to the system to ensure that they have adequate amount of spinning mass on the system to ensure that there's enough inertia in the instance that some kind of event would occur and frequency would need to be arrested. Now, we should point out that spinning mass is not the only way to ensure that we maintain frequency stability. But this is definitely the more traditional ways. And so as we transition to a system with more inverter-based resources, system operators have found it useful to understand what their real-time system inertia is. So we're going to hear from a number of speakers on that today. But first, I'll go through some logistics for the webinar. Please make sure as you join the webinar that you have your camera off and you stay muted throughout. There is the opportunity to send questions at any time throughout the webinar this morning. There's a Q&A box on the side of your screen. Make sure that you select the Q&A box and submit the question to all panelists. And we'll make sure that we track those questions and get them answered either after presentations or during our Q&A sessions at the end. There is a chat box as well, but we'll only keep that for general comments and not for questions. Please submit your questions to the Q&A box. There's a variety of ways that you can view the webinar tonight with WebEx. So make sure you play around with the layout options if you want to see the speakers in a different way or see the slides in a different way. If you're having audio issues, make sure you check your audio inputs and outputs into your computer. If you're listening by your computer and you're having some trouble, you can always try dialing in by your phone. And if you're listening through your phone, there is the option to try using your computer as well. This event is being recorded, and we will post it in the coming days on the G-PST website at globalpst.org. We can move forward, Isabel. Here's our list of speakers tonight. We have a variety of folks who are going to first introduce G-PST and then also the Southeast Asia Community of Practice that is going to be incorporated as part of G-PST. And then we'll hear from some experts from a variety of system operators in the region, from EPRI, and then also from Europe. So we'll move on to the agenda. We're going to first hand it over to Sadie Cox, who will give an overview of the G-PST consortium, followed by Benny Suradi, who will be giving an overview of ACE and the collaboration with G-PST and the community of practice. Then we'll hand it over to EPRI, our EPRI expert, Parag Mitra, will be giving a broad overview of inertia monitoring tools throughout the globe. We'll then dive into the experience of two system operators from the region. We'll hear from NLDC and their experience of creating a tool initially in terms of for monitoring inertia. And then we'll hear from PLN from Indonesia to understand their experience. Finally, we'll learn from some experiences and tools established in Northern Europe. Then finally, we'll wrap up with an opportunity to have more engagement with the panelists through a Q&A session. So with that, I'd like to hand it over to Sadie Cox to give us an overview of the Global Power System Consortium.
Great. Thank you so much, Josh. And thank you all so much for joining us this evening or this morning, depending on where you are. It's fantastic to have such a large group joining in this peer learning webinar and for this launch of the G-PST Southeast Asia Community of Practice. So moving on to the next slide. So hopefully many of you are already familiar with the G-PST, but if not, I wanted to provide a quick introduction to kick off the webinar. So the Global Power System Transformation Consortium, or the G-PST, is all about deep collaboration with leading system operators around the world on cutting-edge research to bring the highest levels of variable renewable energy onto the grid, as well as provision of technical assistance, knowledge sharing, and peer learning on proven operational and engineering solutions to advance renewable energy integration in unique contexts all around the world and to address key challenges. So through the G-PST, we're working with many partners across many regions around the world. And on this graphic in the middle of the slide, you see our partners kind of laid out. So we have our founding system operators, or what we call our FSOs, which includes California ISO, AEMO in Australia, National Grid in the UK, EirGrid in Ireland, Energinet in Denmark, and ERCOT in Texas in the United States. And they're really focused on coming together to identify the most cutting edge research areas and related R&D investments required to reach very high VRE, as well as working with peer system operators all around the world to support them in scaling up RE integration. In addition, we're also working with a group of core team institutions, which includes the ASEAN Center for Energy, and you'll be hearing from Benny in just a moment, CSIRO in Australia, the Electric Power Research Institute, IEEE, and several others on both the research piece that I just mentioned, as well as on our support to emerging economy and developing country system operators on adapting technical solutions to really transform their power systems in various ways. And so on the slide in the center, you can also see our G-PST partner countries, which includes Indonesia, Vietnam, India, South Africa, Tanzania, Peru, and Morocco. And we're aiming to work with around 15 countries in the first year with support from several different organizations. So together with our G-PST partners, we're supporting system operators through our 5 action pillars. So pillar 1 is led by the Energy Systems Integration Group, and that's where we're bringing together our founding system operators to develop a research agenda on the most forward-looking research areas to support high VRE penetration. Pillar 2 is where the core team and FSOs are working with our emerging economy and developing country system operator partners to provide deep technical support through targeted technical assistance and fellowships, really focus on advanced operational and engineering solutions, as well as broader peer learning at the regional and global level. So for example, through this community of practice. Pillar 3 is coordinated by Imperial College in London, and it's focused on improving and applying cutting-edge educational materials and courses at the university level, as well as upskilling the current system operator workforce with continuing education. Pillar 4 is coordinated by IEEE and is focused on supporting countries on technology standards, certification, and testing, and really localizing technologies to very unique contexts. And then finally, Pillar 5 is coordinated by VTT in Finland and is focused on improving and disseminating best-in-class open tools and data to support system operators with various types of key analyses to enable grid integration and providing technical assistance to system operators to apply these tools in very specific contexts. So moving to the next slide, we're very keen to invite everyone on the webinar today to join this new G-PST community of practice that we're launching today, together with the Asia-led partnership with a focus on system operators in Southeast Asia. And so the community practice is being led by one of our key G-PST partners, which is the ASEAN Center for Energy. And again, you'll hear from Benny on their role in just a moment. And the community practice is really focused on bringing together system operators in the Southeast Asia region specifically, together with our founding system operators to share lessons and good practices on advanced operational engineering solutions to enable higher VRE integration. So the community of practice will be focusing on provision of these types of peer learning webinars, trainings, and online moderated discussions. And that'll be all based on surveys in the region and determining the topics of most interest. We'll also be providing some light touch technical assistance opportunities for more specific support to various system operators in the region. We'll also be developing some knowledge products on various case studies, different types of good practices that can be highlighted in the region and that sort of thing. We're already planning for our next community practice event, which will be on August 25th, and it'll be focused on renewable energy forecasting methods. And we, again, invite you all to join in this community practice and to continue to engage with us through this community. And here's an email address if you would like to continue to be involved. So I will stop there and hand it over to other folks that are on the webinar to dive into the technical topics in more detail. But thank you all so much.
Great. Thank you, Sadie, for the introduction to G-PST. And now I'd like to hand it over to Benny Sarati from the ASEAN Center for Energy to give us an overview of the energy transition and how G-PST and ACE can collaborate through this community of practice. Benny?
Yeah, thank you, Josh. Thank you, Sadie, as well. Good morning from Jakarta, everyone. To dear colleagues and friends, for all of you who are joining with us in this important discussion. I'm really excited this morning. I learned that we have around 200 more colleagues registering for our event this morning. Many of you are coming from the Southeast Asia region, but also a lot of you are kind enough to stay late or wake up earlier to join our discussion today. As Josh mentioned that today we are having a webinar for the discussion on tool and case studies for inertia monitoring and calculation as part of our Southeast Asia G-PST community practice, as Sadie also briefed before. Many of participants today are from the key power system operator in the region. However, we also learned that many participants are coming from the research and educational institution, government, business, and other stakeholders in which we are very keen to collaborate under this consortium to accelerate the clean energy transition in the region. For the next few minutes, I would like to brief about the energy transition in ASEAN, ACE, and the G-PST. Next slide, please. Next slide. Our collaborative effort in this region, an integrated activity of the 10 countries in the Southeast Asia, is guided by a regional blueprint on the energy cooperation called as the ASEAN Plan of Action for the Energy Cooperation, or APAC for short. This is a 5-year plan endorsed by the Minister of Energy from all of 10 countries in this region, which drive the goals of the region to achieve the energy security, energy accessibility, affordability, and sustainability for all. It has 7 focus program areas. But 2 points that I would like to highlight this morning is one on the ASEAN power grid, where we in ASEAN would like to expand regional multilateral electricity trading, strengthen grid resilience and modernization, and promote clean and renewable energy integration. Second is on renewable energy, where we in ASEAN will aim to achieve its aspirational target of 23% of renewable energy in the total primary energy supply and 35% of renewable energy in installed power capacity by 2025 through deploying large-scale renewable energy system, accommodating a higher share of renewable energy in the ASEAN power grid, increasing RE investment, and also exploring new and emerging energy technology. Next slide, please. The ASEAN Center for Energy, the institution that I'm representing, is exists to support the ASEAN country to achieve the goal that I mentioned earlier. We act as a think tank, we act as a catalyst, and also a knowledge hub on the energy in this region. But we do realize that this is something that we can't do alone by ourselves in this region. This is why ACE is very proud to be part of the global consortium on the power system transformation. As you hear previously from Sadie, that it has a lot of expertise joining hand under this global consortium. And what I would like to also emphasize is, with the involvement of ACE as a regional lead for Asia in the G-PST through various research, various activity, including what we are organizing today, we are bringing global force and expertise to accelerate the clean energy transition at the ambitious scope and scale that is required in the Southeast Asia. We are bridging it with the various system operator in the Southeast Asia country, to the HAPWA, to the head of the ASEAN Power Utilities and Authority, the recognized electricity organization in the Southeast Asia region, in which PLN and EVN also the members, and of course to the government, to the policy makers from all of the 10 countries in this region. So once again, welcome and thank you very much for joining with us today, and wish you all a very fruitful discussion. Thank you, and back to you, Josh.
Great, thank you very much, Benny. I'll hand it right over to our first technical speaker. We have Parag Mitra from the Electric Power Research Institute, who will be giving us an overview of inertia monitoring practices throughout the globe. Thank you, Parag, for joining us, and take it away.
Thanks, Josh. I hope you can hear me fine.
Yeah, it sounds good.
Great. So let's move on. And today what I'll do is I'll give an overview of the various inertia monitoring techniques that are kind of popular around the globe. So we can move to the next slide. So yeah, before we start this presentation, I really wanted to acknowledge the work done by my colleague, Tapia Dattare. She was with us with Inertia for a while, and she contributed significantly to this work. So it's only appropriate to mention her before we move on. So yeah, let's move to the next slide then. Okay, so this presentation we are going to talk about inertia and inertia monitoring. So it makes sense really to understand what is inertia and why it is so important. So inertia is actually a property. It's the property of an object to stay in a state of motion or in a state of rest. Newton coined this term way back in 1686. So of course, it's a property. It's not a measurable quantity. So what is the measurable quantity? The measurable quantity is the moment of inertia. This is a quantity that is dependent on the mass and the geometry of a rotating body. Its unit is in kg meter square, and if you want to think about it, this is the equivalent of mass for rotational dynamics. So if a thing is moving on a flat surface, we say force is mass times acceleration. But if it's rotating, we say that the torque is equal to the moment of inertia times the angular acceleration. So it's the equivalent of mass. Now, if we were to write down the equation of a rotating machine and then do some normalization, this equation starts to look like something we have in the box on the left-hand side of this slide. So the term 2h over there, the term h marked in red, that is what we call the inertia constant. And this is a term that is derived from the moment of inertia. And this term, or this quantity h, is what helps us sort of estimate the inertia or the property of an object to stay in a state of rotational motion. So this is the term, this is the quantity that helps us estimate that. And in this particular presentation and in general in our power system practice, this is the quantity that we want to estimate. So why is this quantity important, and why do we want to estimate it? So if you look at this plot that we have in the center of this slide, you will see it shows how the system frequency changes when you have a disturbance on your system. Now, when the inertia starts to go down, you see that the frequency decline is faster, which is shown by the red curve over there. So the rate of change of frequency increases. And you also see that the frequency trajectory sort of has a lower nadir. So what is the main takeaway? If a system has low inertia, it can be exposed to unacceptable rates of change of frequency that can trip some frequency sensitive relays, or your frequency of the system can drop below a certain level, and that can trigger under frequency load shedding in your system. So because of that, most utilities are concerned about what is the inertia of the system, and essentially everybody wants to go ahead and try to get a sense or try to estimate what that value of H is. So moving on, which elements provide rotational inertia in our system? So the rotational inertia in our system typically comes primarily from conventional generation plants. So these are nuclear plants, coal plants, combustion turbines, combined cycle plants, and hydro units. Now, most of these units, they have these inertia constants in a closed range, and I've sort of tabulated them on the table over there, with the exception of combustion turbines. So there are typically two main categories of combustion turbine. One is what we call the aeroderivative turbines. These are essentially the gas turbines that are hanging on the wings of a Boeing 777. And then we have the single shaft industrial gas turbines. So the aeroderivative turbines, they typically tend to have very low inertia because they have the low pressure turbine on a different spool. So those are the ones which will have inertia constants from between 1 and 3 somewhere. The industrial gas turbines, on the other hand, are these huge machines, and they tend to have very high inertia. So they will be sort of on the heavier side of the spectrum. Apart from these conventional generation plants, we also get some form of inertia contribution from the motor loads in our system. It is not comparable to the amount of inertia you get from conventional generation plants, but it still provides some sort of inertia over there. So you can see that there are typically 3 main categories of motor loads on your system. These are fans, pumps, and compressors. And I've sort of listed down the inertia constants of these different loads. And finally, we have this third equipment that provides some inertia to the system. So these are our synchronous condensers. Now, again, synchronous condensers can have a very wide range of inertial contribution. It can be very low in the range of 1 second. These are just our simple synchronous condensers. And then now you have new options where synchronous condensers come with flywheels, and they can contribute to inertia in the range of 9 to 10 seconds, which is essentially significantly high. So those are the elements that provide inertia. Now, what doesn't provide inertia to a system? So all the generation that is converter interface, so things like the wind units, PV plants, or energy storage that is interfaced through a converter, they do not provide any inertia to the system. Electronic loads like televisions or LED lamps, they do not provide any inertia to the system. Variable speed drives, which may run a lot of motoring loads these days, again, these do not provide any inertia to the system. And incidentally, what we are seeing moving forward is that the penetration of these devices, converter interface generation, electronic loads, variable speed drives, these are increasing more and more in the system. So we are essentially looking toward the system in the future where the inertia is expected to decrease. And again, that highlights why we want to monitor the inertia of the system. So moving along, we have to ask this question then, what is the system inertia? Now, if you look at this example system over here, you can see it's a network that is connected with multiple transmission lines. So a system like this is expected to have multiple interconnected generators. Now, each of these generators will have a different inertia constant. And if you have an event on your system, the frequency dynamics looks like something that I have on the right-hand side of this slide. So all the generators tend to oscillate around each other in coherent groups or some non-coherent groups. They tend to oscillate around each other, and they tend to follow this sort of this bigger profile that you can see the frequency dips and sort of settles down this way. And the question is, if you were to measure the frequency at each of these generators, and then if you were to compute the inertia constant, you would get the individual H numbers for each of these generators. So what is the system inertia? We know the individual inertias. What is the system inertia? So the system inertia is actually some weighted average of all these different inertias. This is typically measured in seconds, or you can measure it in megawatt second or MVA second, which is essentially a unit of the rotational kinetic energy in the system. So these it actually serves to tell you how much inertia you have on your system, or overall how the system would behave. Right. Now, if you were to measure the frequency at some of the high voltage or some of the EHV buses in your system, you wouldn't get the inertia of a single machine, but you would start to see some sort of weighted average of the inertia of the system. So if you're measuring the frequency at any of the high voltages or any of the EHV buses in your system, and if you were to compute the inertia corresponding to the frequency, that inertia would be somewhat reflective of this weighted average of individual inertias, which in turn would be the system inertia. Now, why do we want to measure the system inertia, and what does it tell us? So the system inertia tells us on an average how the system frequency response will look like, with an understanding that all the other machines will move very close to this system inertia profile, right? So if we were to look at the system frequency, which is defined by the system inertia, the understanding is that all the machines in the system would move very close to this. And if I were to make, or if I were to draw a decision or make a judgment on if my system was to run into a frequency problem, just looking at this frequency corresponding to the system inertia, I would be able to make a good decision as to whether my system runs into a problem or not. So this is the quantity system inertia, and this is the quantity that we are trying to monitor. And if we move to the next slide, these are essentially the methods that are available to us today to monitor the system inertia or estimate it in some way. So if we look at the different methods that are available around the world, different practices that people follow around the world, we can sort of categorize them under these three different categories. So the first way of monitoring the inertia is by looking at the unit commitment from the energy management system. And this is a very simple method. I'll get to it in a little bit, but this, you can measure the system inertia or get some sense of the system inertia in real time. The second way to monitor this is a continuous signal-based method. Now, there are two different categories of it. One is by measuring the ambient frequency of the system and measuring the ambient power of the system, and then trying to estimate the system inertia out of it. The other one is an intrusive method where you try to inject small perturbations into the system and then see the response of the system, and from that response, we try to estimate the inertia of the system. And then there is this third method, which is called event-driven. And this can be of two types. One is after the fact, and one would be in real time. So after the fact would be the postmortem analysis, where you would have a large event on your system. You would see the frequency decline. You would do some sort of analysis to find out, based on the event size and the frequency decline, what the system inertia is. And the real-time analysis is essentially trying to measure what kind of power imbalances you see in a certain region, and then look at the frequency changes because of the power imbalance, and then try to estimate the system inertia out of it. So these are essentially the three different categories, and what I'll do today is go through each of these categories, give you some idea of what goes in each of these methods, and then try to tell you how probably one group of methods are better than the others in certain situations. So moving to the next slide. Yeah, so the first method is this method called the unit commitment-based inertia estimation. So how do we do this? So if you had an EMS on your system, you could look at all the units that are online. And if you knew all the units that were online in your system, one way of computing the inertia of your system would be to multiply the MVA rating of the unit to the nameplate inertia constant of that unit, and then sum it over all the units in your system. Now, this is a method that is followed fairly in many parts of the world. We have some examples on the slide from ERCOT and FinGrid. where they use this method. They essentially look at the hour-to-hour unit commitment, and then they use the simple formula to compute what is the inertia of the system. The method is simple. It provides you a good estimate if your system is much contained and you don't have a lot of ties with your neighboring systems. And it is also convenient for real time. And if you know some forecasts of what your unit commitment will be, you can sort of forecast the system inertia for different time frames. So it's a very convenient method to do that. But this method has some drawbacks. So if we move to the next slide. Yeah. So when does this unit commitment based method not work as expected, right? So even though it's a very simple method, there can be instances when this method does not work as expected. So here are some examples when this method might not work well. So if you have substantial inertial contribution from distribution side resources. So if you have, let's say, a large gas turbine which is in a captive industrial facility, or if you have a large gas turbine which provides district heating, and this is not monitored in your EMS, you will not be able to account for the inertial contribution from that particular generator. So if you're using a method like this, which depends on the unit commitment that can be seen from the EMS, of course, you won't be able to account for this. And a good example of this is the National Grid UK. So this system has a lot of district heating, which is done by using large industrial gas turbines. And typically when they estimate the system inertia from the EMS measurements, they have to sort of use a scaling factor, which they use to scale up the system inertia. So they don't capture all the inertia that is coming from those gas turbines in the distribution side, and essentially they have to scale it up. So, and to do that, it takes a bit of a practice. You have to look at some events, you have to see what you're measuring, and then kind of estimate what the scaling factor is over a period of time. And then you go ahead and you scale it up so that you have a better idea of what your system inertia is in other periods. The next instance when this method might not work as expected is if you have a lot of ties with the external system and you do not have visibility of the unit commitment over those ties in your EMS. So you are a system which is strongly connected with your neighboring system. Your EMS only has information about the generators in your system. If you use this method, you won't be able to account for the inertial contribution that you might get from your neighboring system. So that's one place where it fails. And the third one, which is really a very important point that is coming up as we move on to high inverter penetration, is if you have loosely coupled generation areas within your system. So with this method, you're going to estimate the system inertia, but if you have loosely coupled generation areas in your system which have low inertia, you might not be able, or rather the inertia estimate that you get by this method may not be very useful for predicting if you have a frequency problem in your system. And to understand this better, let us go to the next slide where we have an example to see how this thing looks like. So what is this regional issues with loosely coupled system? And to motivate this, what I did was I used this simple example of 5 machines connected through some transmission line. Now, this might look like a very simplistic example, but just to assure everybody on this call today that this system, which is a very simple system, 5 machines connected by a transmission line, a simple system like this can be actually used to describe the frequency dynamics of the entire Western United system for a loss of 2 large nuclear power plants. So even though this system looks simplistic, it is very powerful in explaining some of the frequency dynamics that we see in real life big power systems. Right. So now let's get into what happens or what this regional issue with loosely coupled system is. So if you look at the curve, or if you look at the system which is on the very left side, you will see that we have 5 generators These are connected through pretty strong transmission lines. You can see that the susceptance of these lines are around 800, which means it's a very strong connection. And all of them have similar inertia. Now, if I put a disturbance on the very end of the system, the frequency dynamics looks like what you have in the plot below. The black curve that you see over there is your system inertia that is measured or the system response corresponding to the system inertia that is measured by the unit commitment method. What you will see is that all the generators oscillate around this black curve, but they are pretty close to that black curve. So the black curve sort of dips all the way down to very close to 59.9, and the largest deviation goes down to 59.85. So if you were to look at the black curve, it essentially tells you on an average how the system behaves like, and it's a good approximation of what the system frequency response would look like. But if you move to the system to the right of this, you see that when the inertia of the last unit, G1, goes down from 6.5 to 1.5, the inertia goes down, and this can go down because of a whole host of reasons. You can have a significant amount of renewable resources coming in that region, which might pull that inertia down. Now you see that things start to look very differently. The blue curve that you see in this plot is the frequency of that particular system. And you can see that the frequency of that particular system oscillates wildly and is quite different from what the black plot shows you, right? So now you might start having frequency problems in your system that the black plot might not show. So what we can conclude from here is that the system inertia right now is not giving you a good measure of the kind of problems you might see in your system. And then if you look at the system on the very right of this particular slide, you will see that the inertia has gone down, and we have also weakened the transmission link between that. Essentially, we increased the impedance to 10 times of what it was before. And now what you can see is that the blue plots, which is the frequency of this system on the very right, it deviates wildly from that black response. So what is the takeaway from here? The takeaway from here is that if in your system you have renewables coming up within certain parts of your system, and a portion of your system has inertia going down, and if you have weak electrical connections to that particular system, maybe it's a remote area where you have a lot of wind or a lot of solar, you may have regional frequency dynamics that may be significantly different from system dynamics. And when things like these happen, a measure of the system inertia based on these EMS unit commitment, it might not give you a good measure of the problems that you might have in those particular regions. So then it starts to make sense to try to essentially find out methods that you can use to look at the inertia of a particular region and consider that separately from the inertia of the entire system. So how do we do that? How do we essentially look at inertia of a particular region in your system rather than trying to find out the inertia of the entire system? So to do that, we have to look at the second class of methods. And if we move to the next slide, these second class of methods are what we call the continuous signal-based methods. So really, there are two categories of these methods. One is an intrusive type method, and one is what we do from ambient data, which is non-intrusive. So what is this intrusive type method? And this has been sort of implemented by this company called Reactive Technologies, and I'll sort of give you an overview of how this thing works. So the intrusive method involves injecting a modulated signal, a modulated power stimulus into the grid. Now, the injected signal typically is not high enough to cause a major disturbance in your system, but it essentially excites certain nodes in your system, and you can see some change in frequencies in your system, which are sort of in the same or sort of has the same frequency of this modulated signal that you're injecting, right? So you have an injected signal, and you can see the response of the system and the system frequency, and you can extract that response out by using some signal processing techniques. And then you can use the simple swing equation. You can essentially assume that the system is represented by this simple swing equation, and then you can go through the signal processing methods, and essentially you can estimate the system inertia. Now, the method has been demonstrated by Reactive Technologies for National Grid UK, and I believe they have a few more projects on it. This is a good method, but then again, this is an intrusive method that requires you to inject some sort of a small disturbance into the system. The second category of methods is based on ambient data. So what does this method do? It looks at the power changes in your system. It continuously monitors the power changes in your system. It continuously monitors the frequency of your system, and essentially based on the deviations of power and the changes in frequency, it applies certain Rmax-based models to create a system model, and from that system model, it tries to estimate the system inertia. Now, there are some drawbacks of this method as well. Sometimes these ambient changes, they are not significant enough to extract the system inertia, so you might get some false numbers coming out of this method. In addition to that, we also have some limitations with our measurement capability. So if you're measuring it with a PMU, there are certain delays associated with it, and you might have to look at advanced signal processing techniques to sort of obviate those measurement delays and try to estimate the real inertia of the system. So moving on. So EPRI is actually doing some work on this ambient data-based estimation. So at EPRI, we have been looking towards developing this particular framework, and what this framework does is it essentially captures, or it essentially takes the PMU measurement. So we take the power, we take the frequency, we do some signal processing to find out the power or the accelerating power in the system and look at the corresponding frequency changes. We try to fit it with an Rmax model, so we do some system identification. And once we have fitted it to an Rmax model, we use that Rmax model to estimate the system inertia. So this method, we have been working on this for some time now. It uses a sliding window technique. It does give us a good estimate of system inertia right now. And if we move to the next slide. Yeah, this is how this toolbox looks like. We are still developing this toolbox, but you can see that we can read in PMU data. We can look at the power deviation. We take the frequency measurement, and we continuously create an Rmax model. And from that Rmax model, we essentially put in a step response, a step to that Rmax model. And based on the changes of the frequency output of that Rmax model, we can estimate the system inertia. We have done some demonstrations for certain systems. Until now, what we've seen is we do get some good results. Okay, so let's move to the next slide then. Yeah, and this sort of brings us to the last measurement method. These are the event-driven estimation methods. So of course, the first one is the postmortem method, where we have large disturbances. And if you have a large disturbance, you can see the disturbance size, you can see the system frequency. Then you tend to treat the system as a single machine equivalent. And then if you use the swing equation with the formula that I've listed over there, you can easily compute the system inertia. And finally, the other technique is based on real-time measurement, and GE essentially worked in the Migrate program in EU to show how this method works. And the way this method works is you have some measurements of frequency at some of the major buses in your system. At the same time, you measure the flows on the tie lines, which gives you an estimate of what the power imbalance in your system is. And then you can essentially, again, go back and use the swing equation to find out, based on those two quantities, what the system inertia is. So Josh, move to the next slide. Yeah. So I won't go through this table in details, but this table sort of tabulates all the different methods that I spoke about. And once you have the slide deck, this is a very easy lookup table to see what the different techniques are, what inputs it requires, what output it provides, and what might be the possible drawbacks of each of these methods. And that sort of takes us to the last slide, where I have a few quick takeaways. So some final thoughts here. Inertia estimation, this is going to become more and more important as we have more and more converter interface generation in our system. Simply because the system inertia goes down and we are more susceptible to frequency problems, we will need better methods to estimate the system inertia. Like I said, the EMS methods, based methods, these are powerful, these are very simple, but moving forward, these may not be sufficient. It depends on your system, it may not be sufficient. So the system inertia, this is really a metric that helps operators estimate whether the system will have risk or not. So real-time measurements, these are expected to be the best methods moving forward to provide a better measure of system inertia. These are essentially more suitable for estimating the inertia, effect of inertia pockets in your system. When you have large systems with inertia pockets, it can provide you some effect of the impact of load. And it can also give you some estimate of the new things that CIGs may provide. These are virtual inertia and synthetic inertia. So these real-time measurement methods actually help you capture those. So that's the last slide I have, Josh. Back to you.
Terrific. Thank you very much for that great presentation. We do have just maybe a minute to get answered a few questions that came up during the presentation.
Sure.
The first came from earlier in the presentation when you're describing what the various technologies, their inertia constants. So the question is, why do combined cycles and turbines have such a wide range of H?
Okay, that's a good question. So if you look at the aeroderivative turbines, the ones that you have on the wings of Boeing 777, so they have the low pressure turbine on a different spool. So the low pressure turbine and the high pressure turbine is not on the same spool. Now, what happens because of that? If you have a single shaft with a turbine, the H of the turbine actually depends on the size of the turbine blades. If you have the LP and the HP on different shafts, the inertia of a gas turbine is essentially driven by the LP section, which has very large blades. Now, because the blades are on different shafts, the contribution to the inertia is significantly less for aeroderivatives. If you were to look at industrial gas turbines, everything is on a single shaft. The LP, the IP, and the HP, they're all on single shaft. And the LP section, which has very blades with very long radius, they contribute to the inertia. And that is the reason why industrial gas turbines tend to have inertia constants in the range of 6 to 10. Whereas aeroderivatives will have inertia constants in the range of 1 to 3.
Great, thank you. And maybe one other quick question, because I think it's relatively technical and kind of goes back to the slides. There was a question on page 20 about what B12 stands for, and that was where B12's changed from 800 to 80. I'm not sure if that's something that you are able to answer quickly.
Yeah. So B is essentially the inverse of X. So if you have an inductance X, 1 by X is B. So you can do the math over there and see what the X would be corresponding to that. X is the impedance of the line. This is assuming that this is a DC system. You don't have any resistance and everything is reactive.
Great, thanks. And Julia, let us know if you need some more clarification on that. We can get more discussion of this slide in the Q&A session if we'd like. But with that, I would like to move on to our first speaker from system operator in the Southeast Asia region. So we're going to have Mr. Phuong Dang Huy present to us from the National Load Dispatch Center in Vietnam on some of the estimations and monitoring that they have implemented in their control room. Mr. Huy, I'll hand it over to you. Thank you.
Well, thank you, Josh. You can hear me well, right?
Yes, we can. Thank you.
Yes. Okay. Thank you, Josh. Thank you, everyone, and hello, everyone that taking part in the event. So, my name is Huy. I'm from the national load dispatch center of Vietnam. And today I'm very interested and grateful to be here to represent the NLDC to have some of the to present the experience of inertial estimation and monitoring in Vietnam. So we would like to thank G-PST consortium and the others party involved for this event, so that we can have the chance to exchange ideas and learning from each other in this topic. So move on to our slide. I would like to summing up some of the contents here. We will introduce our methods of inertial estimation that we apply in our country. There will be online tool and an offline calculation of inertia. And we also develop some kind of relation between power, frequency, and inertia to have some additional features on our tools. And the last topic will be summary. So the next slide, please. Okay, so next, please. So the first content will be the methods that have been applied in our country. So actually there are two methods that we apply in Vietnam for the moment. I believe that these the methods is also applied widely in the world, based on it easy to be implemented based on the existing facilities that the control centers normally have, which is the SCADA EMS system and the PMU VAMs. So the first method is to summing all the inertia from synchronous generators. Of course, we have the inertia constant from generators, the MVA, and then when we are summing up all of the data, we can have the estimation of online inertia. And this brings the advantage of online and continuous data, but the disadvantage of that is the result is approximate, because the small generators and loads are not considered in this approach. And this approach also depending a lot on the SCADA quality, which also have a big factors in the accuracy of the estimation. Next slide, please. Yeah, so for the second method, which is based on events, we also doing some event postmortem that we calculate the inertia on the events. So after the event, we have the megawatt loss, the rate of change of frequency, and and from that we can calculate the inertia for that event. And so this advantage of this method is that it covers all of the inertia from every device, but the disadvantage is that it is offline, and there are quite problems when we can exactly determine which is the accuracy rock-off. Next slide, please. Okay, so moving on to our online tool for inertia calculation. So this is the formula that I have mentioned. When we have inertia constant and the MVA of the generators, we can summing it up. And to determine the state of connecting of generators, usually there are two ways. One is to use the output power. One is to use the state of the circuit breaker terminal circuit breaker. But in our country, we prefer the output power, because the circuit breakers, sometimes we see that there are some of the generators that don't provide the exact good quality of the circuit breakers, which can cause the inaccuracy to our results. That's why we prefer the output power, and the criteria for generating and condenser of the generators is shown in the slide. And of course, like I have mentioned, this methods has some disadvantage, and the assumptions are shown in the slides. Next slide, please. And so with that tool, we build that on our system, SCADA EMS system. Our SCADA EMS system is from OSI from America, and we build that by developing in the customization programming platform. And this value is we put it into we call it SCADA key. And this SCADA key can have the historical data that we can extract the data every time that we want. And we also displaying the values calculated online for system operators. And whenever the system inertia is lower than the minimum inertia, then there will be an alarm for system operators. Next slide, please. And so for the minimum inertia, the method that we use to determine the minimum inertia is to determine the minimum configuration of generators for critical scenarios of power system. So we choose a very critical time of system, which is the holiday when the load is going down and the high penetration of renewables. And we build the minimum configuration for generators to meet that that demand. And after that, we do a simulation of testing for that configuration. We do a generator fault, simulation of generator fault, and whenever the frequency after the fault is been above 49, which doesn't cause load setting, and the rock-off is less than 0.5 Hz per second, then we determine that that is our minimum inertia for system operation. And the result that we have is about nearly 90,000 megawatts seconds. Next slide, please. And so this is the result for a typical week in March 2021 this year. So normally our inertia values are quite well above the minimum inertia throughout the week. Next slide, please. But for the holidays, you can see that for the holidays I mentioned, which is the biggest holiday in Vietnam, which is the Lunar New Year, happens in February. We have the inertia coming down nearly to the minimum inertia that we have calculated, and that is the time that we can actually test our calculation if it is acceptable or not. Next slide, please. So after that event, we have some post-analysis on the time of holidays. So you can see that in the above is the fluctuation of frequency that we calculated by the function in Microsoft Excel, and the lower part is the inertia. So whenever the inertia is coming down near to the minimum line, which is usually at the noon time when load is very low and solar is a lot, then we have the problem that you can see that the fluctuation of frequency is much higher than the normal time. So from this analysis, we believe that our tool can be possible to assist the system operators in real-time operation, and the result is relatively acceptable, and it can be used as an indicator for system operators. Next slide, please. Okay, so from the online results that we have, we also trying to build a power frequency and inertia relation model development. Go ahead, please. And the methodology, we study it. We learned from the NTSOE report on the inertia monitoring in Europe, and from the swing equation that everyone knows, it can have a linear relation between the change of frequency and the loss of power and the grid inertia, the online grid inertia, which the formula is shown in the slide, the blue color formula. So, so there are three values here, three variables here, and two coefficients. The K and M is the coefficients that we need to be identified using historical data of the system. And for three variables of delta F, P, and inertia, when we fix two of the variables, then we can estimate the third one, the last one. Next slide, please. So with our historical data, which is the dot in the picture, we using the linear regression model provided in Microsoft Excel, so that we can have a fit line of those data, and then from that line we can determine that the function for our system is somewhat mentioned in the slide with the function in red color. This is updated in April this year, and of course, I think that we still have to take more data and update more events so that the line fit line can be represented for many more events. So the quality of that line is determined by the correlation coefficient, which in our case is about 0.76, and it is the best if it can be near to one, to value of 1. And we are also having work is going on to improve this correlation coefficient. Go ahead, please. So from that function, like I have mentioned, when you have two variables fixed, then you can estimate the others. So from that, you can have additional functions for the system operators, like to forecast the frequency nadir for contingency of loss generators. And the display that we shown for system operators is in the slide. So we have different levels of loss generators: 300, 600, and 1200, which is based on our biggest capacity of the system is 600 megawatt. So for each case of contingency, we can forecast the frequency nadir. Of course, the assumption is that the level of primary frequency response is somewhat the same, but this is the indicator for system operators in their real-time operation. And the others, you can also doing some other forecast, like not forecast to determine some others values like megawatt loss, which can cause the loss setting, and the minimum inertia to avoid load shedding with different case of megawatt loss. So this method is also have the ability to determine the minimum inertia, which adds to the method of estimating minimum inertia by offline methods that I have mentioned in the first slide. So we are now having two methods of determine the minimum inertia. One is by event, and one is by the by this use of this function. Next slide, please. Yeah, so we moving on the offline calculation of inertia, which is based on the events. The methodology of that is from the swing equation that you have seen in the slide. And the assumption is that when there is a generator fault occurs, if we can ignore the load damping right after the fault, and also when the primary frequency control is not operated yet, then we mostly the frequency is will be based on the inertia. So we can have the formula as shown. And with delta P that we know from the event, which is the loss of the generator megawatt, and with the frequency and the rock-off that we can measure using the WAMs, then we can determine what is the grid inertia on that event. Next slide, please. So for these methods, the most challenge that we have to face is that how to determine the correct and accuracy rock-off. And you can see that for an event that we have seen in our system, when we get the readings from WAMs at different locations of the system, you can see that there are quite a difference in the readings of WAMs in a short time. So the one that is in red color is quite fluctuated because it is nearby, very nearby to the location of fault. And with this difference, we will have to have a process to process these difference in terms of frequency reading, so that we can determine the rock-off for this event. Next slide, please. So from literature, we have using the method of center frequency. So this center frequency will calculate the represented frequency of the system by using the weight factor for each frequency reading in the provided by the PMU. So whenever the reading from the PMU is nearby to the place that have a lot of big generators, then it is having the large factor. So after that, when you calculate, when it is applied, and we can calculate the frequency for central frequency, then you can use that as a frequency of the system, and that will be used for offline inertia calculation. Next slide, please. So for choosing the PMU locations for that center frequency, we're trying to find the locations that have large generators, and we also trying to ensure that the location choosing this equal distribution throughout the system, and to cover all of the source like hydro, coal, and gas turbines. And if the PMU is too near to the location of the fault, then if it is too fluctuated, then we can manually take it out of the calculation. So this calculation we can configure online on our WAM system, and the historical values can be stored within 7 days. Next slide, please. So with the result from offline inertia estimation, we trying to compare the value from offline and online estimation, and you can see that for every case, the offline calculation is usually larger than the online calculation by 10 to 25%. So we believe that it is logical, because the online calculation it doesn't cover the small generators and the effect of the loss in the system. So it is logical when you have the offline value is larger than the online. And we will have further studies of doing these methods so that we can have a more reliable result of both offline and online systems. Next slide, please. So coming up to the summary, our NLDC has, like I have mentioned, we have approached several available methods in literature. We are basing on our available infrastructure. We have done inertia estimation for online and offline studies. And the initial results that we have show its effectiveness, and it could assist system operators in real time. So some of the developments will be to improve the reliability of the estimation and to study and approach modern methods like Mr. Parag Mishra have introduced in the previous session. And we will also would like to learn from good experience in this topic. And also we study on the initial contribution of non-conventional source like from wind and battery. So next slide, please. So the literature that I've mentioned, we have some of the reference presented here that we have studied from this reference to coming up with our solution for our country. So thank you for your listening, and I would like to end my presentation here.
Great. Thank you, Mr. Huey. We appreciate the Vietnam perspective. I'm going to ask one quick question. There's a number of questions that come in. We'll leave it for the Q&A later. But the first question that came in was wondering if the system inertia requirement and applied Rockoff, if that is stated within the grid code for Vietnam.
The Rockoff is currently not yet written in the Rockoff for the standard of the Rockoff. So actually, the Rockoff that we have used 0.05 in the minimum criteria is we base on our normally Rockoff, which is about 0.04. And we think that if it go above that, then it should be a problem. So we use that as a criteria for calculating the minimum criteria. But grid code, we don't have that Rockoff standard yet. For frequency, we have the load shedding is starting from 49. So we have 49 is the frequency that we don't want to go down below that. So that is the frequency. It is written in the grid code.
Terrific. Thank you very much. There's a number of other questions that we'll get to at the Q&A session at the end of the presentations. But for now, I would like to move on to our next presenter from PLN. We have Iko Yudo Pramono to present on some of the tools and case studies being used in Indonesia.
Okay, thank you. Josh, thank you. You can hear my voice?
You're a little quiet.
A little quiet, yes, okay. Please, no. Hello, is it enough for still?
It sounds about the same.
Okay. I change my microphone. Is it enough?
That's better. Yes.
That's better. Okay, thank you. Okay, good morning, ladies and gentlemen. Thank you for the G-PST consortium that already giving me opportunity Hello. Is okay? Everybody okay?
Yes.
Yes. Okay. I will continue my presentation. Thank you. First of all, thank you for the G-PST. It's already consortium that already giving us opportunity to present PLN in conveying experience in managing system inertia on our grid Jawa Bali system. Jawa Bali system is the largest electricity interconnection in Indonesia. There is a rare and precious opportunity to us for us to be able to share this in front of the world for system community who are member of the PST consortium. Okay, next. This is our presentation. I will explain about the Bali system overview, and the next is tools of inertia monitoring and calculation that already will use. Case study in our system of the system inertia problem, and mitigation for the system inertia improvement, and the last is the summary. Next. Next. Okay, this is our system in Jawa Bali. We have a peak load 335 megawatts in June 8, 2021. This is peak load is a little bit below, because the COVID is already happened, below than peak load at the 2019. 2019 is already reached 27,998 megawatts. And our capacity right now is 38,550 watt. See, and this is increase more than increase than 2019, and our substation 569, and energy production. You can see this is the energy production getting lower than 2019, before and during the COVID. And the figure show the power flow condition in Jawa Bali system. As you can see, in the load center is the west side of Jawa Bali Island, while lower cost generation on the east and central side. So in the daily condition, there is a large power transfer from east to the central and west Java. Okay, next. This is generation location and composition. We have 38,556 megawatt, and the composition is 58.2% is from the coal, and this is a bigger our composition from the coal, and gas turbine is 30.94%, and this is the composition is will be so the comparison as generation composition before and during 2021. the 2021 is already operation to time 1,000 CES power plant, new power plant that have operating in Jawa Bali system. Ultra critical, super critical. In the next few years, there will be more generation in the same size, will be increase the system stiffness, but the other hand will be create significant frequency acquisition when that generate the new generation already trip. Okay, next. Next. Okay, next. This is a tool for the monitoring calculation that already we use until right now. The existing for the offline, we only use the PSSA for the long-term system planning and the power factory silent for the system operation planning, right? To make a planning daily, and the power plant dynamic testing for the parameter modeling that we use to get the real parameter in our generation to put in the our system modeling in the silent or NPCSA. And the online right now we use statistic data for disturbance that if the disturbance large disturbance happen, we will use the data in AJC, but AJC right now in progress and state estimator in progress that online unfortunately we can monitor in online right now. And the future, we already plan for the new for upgrade our silent for the feature the outstanding power system modeling capability, and for the online, we plan to build advanced control center with dynamic security assessment and also accurate state estimator residual correction by pressure measurement unit. So we want, if any happen in our system, we can detect with the pressure measurement unit and make accurate simulation. And assessment of the real-time monitoring with the wide area monitoring system integrate to the SCADA or EMS system. So in advanced control center, Sonic Valley assists dispatcher in monitor and calculating system inertia online. Okay, next. This is some theory of the inertia like Mr. Frederick Mitra before. It's already he said. Low inertia fast governor, and we can see high inertia slow governor. This is a picture of the inertia. Then describe about the comparison inertia and how the response the governor speed will be make contribute to the system response. Next. This is the philosophy of the ACE. In an interconnected power system, the governor to not automatically restore the frequency to the 50 Hz. Rather, this one done via area control error calculation. Previously, we defined as the difference between the actual real power export from an area and the scheduled export, but it has an additional term that already we can discuss before. We can B is balancing authority frequency bias. So we can put actual scheduling and already frequency bias. Next. This is our system right now. This feature, so the currently on the Jamali system, one system is still operating in standalone basis, or unfortunately we can say this is one still only for the metering, for the measurement, like the measurement, yes, but not controlling. Still, so this is useful for the for evaluation if the system has already large disturbance happen. Next, and this is our control error in our SCADA. We have already control area control error, but unfortunately the data is not correct right now. Okay, so we don't use area control server for the online in SCADA EMS system. But the next, after we already have the all parameter, we can using the area control error online. Next, please. This is our future. This is our future. I mean, we plan and our dream also to get integration BAMs to area control center, advanced control center. Still right now in progress, maybe in 3 or 4 years. The next 3 or 4 years will be operation in Jawa Bali. We can also make forecasting, daily forecasting and dynamic analysis to get the real situation that will be help the dispatcher to be able and monitor and calculate system inertia more precisely. Next. I will share the case study in our system that we have a system inertia problem. Next. In the case one, happened in Jawa Bali in Tuesday, January 13, 2015 at the 10:55 EM. We have the large disturbance in our system that spirit process of the western system with the central and east system. So you can see this is happen because the fault triggered by flashover from the phase conductor to vegetation in first 500 kV transmission line Ungaran Mandirancan due to windy and heavy rain. First speed recluse success, but the fault still happen. So all the 2 circuit will in Ungaran Mandirancan is tripped. As the result, unstable power swing happen or out of tap, cause the Padang Tasik circuit trip, and the Jawa Bali split be lost in west area of the Jawa Bali, lost power 2017 megawatt from the east. How the system respond? Next. This is the frequency system response. You can see this is frequency response. In the green line is the East Java frequency, because the East Java is transferred 2000 megawatt and load 2000 megawatt also, and the frequency become increase until 51.4 hertz, and go to the stable again. And how about the West Java? The Java is lost the generation 2000 megawatt. The frequency decreased until 48.65 hertz. And the Java Bali splitting is until 1 hour 30 minutes. Luckily, the system is going stable. All the two system is going stable. Then we can connect again and 1 hour 30 minutes. Okay, next. Please, next. This is the case 2. I will explain the Java Bali partial blackout on the Sunday, August 4, 2019. Maybe this is the partial blackout is already famous, yes. This is the big problem, large disturbance in our system. Almost the same situation at the before in February 2015, but phenomena, this spirit process is the different. Yes, the chronology, I will explain the chronology. We have more triggering flashover in phase conductor in vegetation on the 500 kV transmission line Ungaran Pemalang. The flashover occur 4 times sequentially between the 21 minutes. By the way, is unfortunately our protection is we have our protection. So the 2 circuit already collapsed, already tripped, yes, and at the same time we have a planned outage in Tasik Kesugian because we have a maintenance scheduling on the transmission. So when the 2 circuit from the Pamalang and Ungaran already tripped, only 1 circuit still connected, Tasik and Kesugian. So 1 circuit is deliver or transfer 2000 megawatt, and this is causing the rotor angle. This will become cause rotor angle between west generator getting extreme and become out of tap. So again, west and the east and the middle is spirited, but this is not like before in 2015. This fault triggering blackout, partial blackout in the west system. Next. Next. Please, next. Next. Okay, this is a frequency response. This is very interesting cases. Back, please. Please, back. No, back. Back. Frequency response in West Java. Back. Back, please. Back. We can back. Please, back to frequency response. Back again. Please, back again. Once.
Correct. Frequency response in West Java and East Java?
Yes. Yes. Okay, thank you. This is interesting frequency response in West Java and East Java. And the blue line, this is a frequency response in the East Java. And the green line is frequency response in the West Java. You can see the green line, the frequency going down until the frequency nadir 48.35 from 49 and 9 hertz. So very deep, yes, because lack of the generation until 2269 megawatt, yes, and our defense scheme, our automatic frequency load setting is already operated in the 7th state until 7th state, and the frequency going rebound to 49.24 hertz. But it is not continuity and going to the normal frequency, but we have the active power withdrawing or outer loop. The frequency going down again, and go down until collapse in 45.5 hertz. This is the interesting phenomena that our system, the inertia maybe is enough, but we have a active power withdrawal that very dangerous in our system right now. And how about the blue one and the east system and the central that already lost the load until 2000 megawatt? The frequency increased until 51.4 hertz and go again because some generation already tripped. Yes. So the system is going to the stable. That our problem in the west side. Okay, next. Okay, this is frequency in the east. You can see this is a frequency in the east. Frequency going up, yeah, up until 51.4 hertz. But our some generator in east also trade that the frequency going down and rebound again and going to the frequency normal. Next. Next. And after the large disturbance, we calculate our inertia in Jawa Bali. In the two large disturbance in Jawa Bali, we can see this is the red and the blue one. And the blue one is we have high inertia and generator also, and the red one we have lower inertia. So in the roadshop we can see the different two occasion, the two disturbance is already happened. As the blue one is better than the red one. Okay, next. And how about the composition generation between the two disturbance? You can see on the left hand side, this is occurred in 2015, and the right hand side is occurred in 2019. We can see the composition is different. You can see in the left hand side we have the fast response more than the right hand side. So when the fault happens, the response of the system is different. Okay, next. And this is maybe is the same before. I will only set this is the stability is depend on critical clearing time and critical clearing angle. So play a very important role to determining direction of the system stability after certain transient disturbance in the system. Okay, next. And we have one case again that we call this is the disturbance in Python power system. This is the in the east part of the Jawa Bali, yeah. That we have a two sites that have a big generation. One in the east, one in the west. In the west is we have 3,600 megawatt in Suralaya, and also we have 3,500 in megawatt complex generation in Python. That I will explain this about the big disturbance in the east. Fault triggered by flashover also in the phase conductor by because the vegetation also in 500 kV transmission line Python Grati. Between the difference between is Python and the two circuit is different 5 millisecond, and the both of the block line is already tripped. So when the trip in the Python Grati, you can see in the Python Grati transfer is 1,400 megawatt, and trip, so 1,400 megawatt transfer move to the Python Kediri that already have 996 megawatt. So maybe 2,000 megawatt from the Python Kediri that trigger the out of tap also, or the power swing in our system. So the Kediri Python in the Kediri the relay protection in the Kediri detect the power swing and trip Kediri Python, so we lose until 2,000 megawatt from generation from Python. Okay, next. This is the frequency response in our system. We captured in frequency, this is frequency we captured in the west side. So I explained in the west side, we lose 2,000 megawatt, but the system respond going normal or maybe back to the normal. This is our system response. Some cases in our system in Jawa Bali. Okay, next. After big large disturbance in our system at the August 4, 2019, our McKinsey, our consultant McKinsey give us recommendation. We do correctly in our system and improvement in our system to get more reliability from the McKinsey recommendation. And next, Next. Okay. And this is we capture inertia system after we already do our consultant recommendation. We can see this is inertia is already better than before. Yes, we lose. Before the fault occur, the frequency is 50.15 hertz, and when the 1,500 megawatt generation in period trip, the frequency going down only to 49.27 hertz. So this is the Suralaya governor free control response. It increased the load to 370 megawatt in 11 seconds, and the phenomena outlook is happen and the generation load decrease, but the system decrease, but until 49 hertz, and the system, but the system is going restoration after fault happen. This is a good because we lose 150, 1,500 megawatt. The system is good, is still good. Next. This is our frequency response and frequency deviation after we already make improvement in governor-free operation and AGC operation. And we can see in 2018 and 2019 and 2020, we can see the 2020 is better, going better than before. That deviation only 1.3%. Okay, next. How about the system reliability? Availability spinning receive to be at least one largest unit online to the system. The largest net capacity in Jawa Bali right now is 991 megawatt in coal generation in we call the Jawa 7, Jawa 7, and Cilacap 4. And the availability spinning reserve that will prepare 50% of the largest unit consists of fast response power plant from hydro and combined cycle gas plant. And on the other mode, where the availability spinning reserve is less than the largest unit, fast response is minimum a 50% availability spinning reserve and the rest of the load shedding. Okay, next. 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 This is a summary as our presentation. We have a lesson learned. The inertia of the Jawa Bali power system is proved to be significant contribution in determining the direction of the system stability after the major disturbance in the system. In Jawa Bali Control Center, improvement will be being made for the system inertia monitoring and calculation for existing application both offline on online SCADA. And the last but not least is advanced control center in Jawa Bali that being developed to answer the challenging QRA penetration, especially by integrating WAMPs into the SCADA or EMS system to gain more accurate online system inertia monitoring and calculation in assisting dispatching to keep system is still stable. Okay, thank you. This is the last our presentation.
Great. Thank you very much for that insightful look into some various case studies from the Indonesian experience. Interesting to see, especially that split of the frequency across the same interconnection. Okay, with that, we're running a little bit behind schedule, so I'm going to pass it directly over to our speaker from Denmark, from Energy Nets. We've got Peter Markussen, who's going to give an overview of the operation and inertia of the Nordic system. Thank you. Peter?
Yeah, good morning, or good afternoon, good evening, depending on where you are. Thank you very much, Josh. I hope you can all hear me and you can see my presentation. I will say a few words on the Nordic system operation and how we have dealt with inertia. And say my focus will be more on a strategic perspective and on the process that we have used in between the Nordic TSOs and less on technical details as have been shown in some of the former slides, but there will be links to reports where these can be found. So next slide, please. So just very short introduction. I work for Energinet, Danish TSO in the northern part of Europe. We operate the Danish transmission gas pipelines. We have to ensure the balance on a daily basis, long term. And we're owned by the Danish Ministry of Climate and Energy and Utilities, and have a vision that we want to have a green energy for a better world. So try to use new solutions and get experience from others and give our experience to others as well. We are developing quite fast with the use of renewables and also especially offshore wind, and are quite well connected to our neighboring countries, as can be seen on the figure to the right. Next slide, please. And just to give some facts on where are we with our green transition, and we today have 64% green electricity in our production, and that is wind, solar, and biomass. Just looking at wind and solar, it's 50%, and 37% green energy system if you also include other use of fossil for transport and other uses than just electricity. Our target is green electricity production of 100% in 2030 and 70% reduced CO2 emissions compared to 1990. So that's quite ambitious, but we are moving well forward, especially with the increase in use of offshore wind, where we have large resources. And as can be seen in the figures to the left, we are also importing quite a lot of electricity at the moment, so there is a lot of exchange between neighboring countries, both with AC links and HVDC links. And when we look ahead, as mentioned, we are going for 100% green electricity in 2030, and that is quite a challenge, both to build the renewable energy fast enough, but also to operate the system. And say for historically, we have not looked that much on inertia, but that is getting more and more important when we look into the future with more distributed electricity from solar and wind. So next slide, please. So just to give an understanding of where what the Nordic countries looks like, we cooperate quite closely with Statnett in Norway, Svenska Kraftnät in Sweden, and Fingrid in Finland, and then Energinet, where we for the last I say almost 100 years, you say the first interconnection between Denmark and Sweden were built back in 1915. So we have for almost 100 years been interconnected with our neighboring countries. And we have for the last 40 years had a very close operational cooperation where there is actually there is also now a common control center based in Copenhagen, where we have a common grid model to be able to do daily analysis on the situation in the Nordic system. Most of the production in the Nordic are from hydro, especially in Norway. Then there is nuclear in Norway, and there's nuclear in Sweden and in Finland. And then in Denmark we have thermal capacity, we have wind, and the wind is and solar is increasing, whereas thermal is being phased out also in Finland, and nuclear is also partly being phased out. There is new nuclear being built in Fingrid, whereas it's more undecided what to do with nuclear in Sweden. But in general, say thermal and nuclear, that are giving us the inertia today, is being reduced. So next slide, please. So when we look at how we operate our system in the Nordics, then it's also quite dependent on, or it's actually regulated by European regulation, and we do have our own synchronous area in the Nordics between Norway, Finland, Sweden, and the eastern part of Denmark, whereas the western part of Denmark is part of the continental synchronous area. Then the synchronous areas are split in low frequency control blocks, where the Nordic is then one large low frequency control blocks, whereas in the continent it's split up between each country. When you have an LFC block, then based on the regulation, you have different obligations. And in the table to the right, you can see these obligations, and especially when it comes to LFC areas and LFC blocks, that is then where you have your, you need to uphold your frequency, and also make sure you have the right dimensioning of your frequency restoration reserves. Whereas the frequency containment process, that's the fast frequency reserves, that's on the synchronous area level. So for example, in the continent, there is a level of around 3,000 megawatt of FCR to be bought in the total continental area, and it's around 2,000 megawatt of FCR reserves being bought in the Nordic synchronous area, to make sure you have the reserves so that you can uphold your ACE, your area control area. This was also mentioned, but was used in Indonesia. So this is the setup. So in general, there is actually no demands for inertia in the European regulation. It is based on the ACE and on the frequency regulation. But both in the continental area, but also in the Nordics, there have been a lot of analysis in the last 5 years, actually, to see what are the challenges for inertia. And in this presentation, I will focus on inertia in the Nordics, but it could also have been on the challenges on the continent. But I think the Nordics more look like the electricity system in Vietnam and in Indonesia when you look at the size. So next slide, please. So when we then have our ACE, then we have the three main services. That's the frequency containment reserve, the fast reserve, the AFR to be activated between 2 to 5 minutes, and then the MFR to be activated in 15 minutes. Then there also is a restoration reserve, even slower reserve, and then there also are fast frequency reserve just being implemented in the Nordics, and I will get back to that later. In the Nordics, we have a combination of both the proactive and the reactive balancing. Proactive in the way that we try to foresee the imbalances in the different, or in the Nordic area, and then activating MFR upfront. But then we have a very reactive setup by the use of the FCR to take the short-term imbalances. Whereas, for example, in Germany or Holland, they use both FCR and AFR much more active, whereas we are using the MFR in the Nordics. Yeah, next slide, please. So now looking at inertia, and there have been a quite intense studying going on in the Nordics for the last 5 years, and what has been the framework has been, so what is our balancing approach, and focusing on the ACE and the use of FCR, but we could also see that there were some challenges in some periods where inertia was quite low, and what was then the impact, and should we then look at changing our way of balancing. And then what are the decisions to take in the control center? What are the necessary tools to be used? Where we have then actually included real-time monitoring to support the decisions in the control center. But we have also then given the control center some possibilities to react then when the inertia is low, for example, with this fast frequency reserve. So it has been a setup where we have looked at how to balance. We need to find out what kind of decisions can be taken in the control center, and then develop the tools necessary. And I think this is quite important, so that you not just start to look at how do we want to just look at how can you monitor inertia. You also need to say what will you use this for? How will you react in the control center if you can see that inertia, for example, is low? So it is quite important to combine this with the challenges with inertia, with how we actually react on the frequency with the frequency research we have. Then we have some criteria, of course, security of supply, where we actually in the Nordics we have different ways of looking at security of supply. For example, in Denmark we have a target saying that we want to have a minimum or maximum 5 minutes in average without electricity for on transmission grid for the consumer. So that's a more probabilistic way of looking at security of supply. Then we focus on reducing balancing costs, and then also reduce the complexity of the green transition. That is to say have a relaxed control center, as we say. Then the challenge with the renewables is that we have increased number of units, high geographical distribution, variability in production. So then how to handle that? That is operation closer to real time. And then this also includes real-time monitoring of inertia. But it could also be then update of grid codes and connection requirements, grid enforcement, but also market developments. And we use the whole toolbox, as you will see. So next slide, please. So just to sum up the process and just to say that this is not just something you do a few months. It is a long-term process when you go from analysis to the solutions, where we started our models and estimation back in 2016, or actually even earlier. But this at least was the main document. Then we had a challenge report describing then what are the challenges and then what are the solutions, and then we implemented a fast frequency reserve from 2020. So next slide, please. So what we did is that we do have a challenge with the frequency deviations in the Nordics. Now maybe this figure to the left is a bit difficult to see, but I think the importance here is the red dotted line, because that's the limit for frequency deviations allowed by the EU regulation. and where we are quite close to this limit when we look at the frequency deviations in the Nordic system. But we could also see that with the use of the model tools that we had, that in some periods we would have quite low inertia. The figure to the right shows the challenges in 2025, and then based on a number of hydrological years. So we used more than 30 years of hydrological data to calculate a number of scenarios for what the challenge could look like in 2025. And so it was assessed that we needed at least around 120, 130 gigawatts of kinetic energy, and here you can see in some periods it could be even lower. So we can see that we probably will have a challenge in 2025. So next slide, please. But then it actually turned out that this inertia challenge actually developed faster than we expected, and actually just here the 13th of June, we had the record low inertia in the Nordic power system. So not that we then can say had a critical situation, but was just very low inertia, and we were a bit surprised by that. But you can see the reason why we knew this was because we have implemented the real-time monitoring of inertia. And also we have just implemented this fast frequency reserve, and as you can see to the right, in the hours where we had the very low inertia, there was also hours where we have a high amount of imports, and we did actually activate this fast frequency reserve, but we activated a bit too early. But that's because we are quite influenced by solar and wind, also in Germany, where we are importing a lot of electricity to Germany. So as you can see on the right, our load is around 35 gigawatts, whereas the production was around 30. So we are importing around 5 gigawatt. So that has then influenced our low inertia situation in the Nordics. So this was in what was a Sunday in the summer, where we have quite low demand. If in the winter, for example, we have peak demand around 70 gigawatt, but then also with a much higher production from both nuclear and hydro supporting the inertia. So this is probably a summer challenge. So next slide, please. So just a very short sum up of the tools and how we estimate inertia. But what we did was that we took a Nordic model based on our existing Nordic grid model and historic measurements of frequency deviation. And as mentioned, we have had a close cooperation in the Nordics for many years. So we also have a lot of data that we can use from back then. When we looked at inertia, and was also very well explained by a representative from IPRI, we used the center of inertia method, tried to look at the system inertia, where we used PMU data from transformer station based in each of the price areas that we have in the Nordics. And then based on that, we have made a validation of this model, and we also made a number of sensitivities where we, for example, looked at what will happen if some of the large nuclear power plants, for example, in Oskarshamn or Olkiluoto, if they tripped. But we also looked on the influence from interconnectors, for example, the interconnector between Norway and Holland, or between Finland and Estonia. So there have been quite a large work here to both develop the model, but also to validate it based on both historical events and with different sensitivities. But as also mentioned, also by our representative from NLDC, it is quite difficult to do these estimations So because it is an approximation of the production, load and HVDCs are not included, and then also some of the historic data that the qualities can be quite or not so good or even bad. So, but all in all, we have developed a quite good model. We have then used that, as you saw, to look at what would the inertia look like in the future. And based on this model, we have then developed an online measurement system incorporated in our SCADA systems based on each large production units that we have, and also then based on real-time information or circuit breaker position to see whether they are produced or not produced. And then based on that, each TSO have then in their own SCADA system, we can then follow the inertia, and even we have used it to produce a forecast for daily procurement of this fast frequency reserve. And then each TSO we follow then the inertia in our own area. But then we also looked at the model to see what should be the minimum level of inertia. And as mentioned, we can see that it's very dependent on the production situation and especially how much hydro that is available in the system, whether it's a dry or wet year. It also depends on the interconnectors. It's very much dependent also on wind, and in the future also even more on wind. But the main target is still based on say the frequency, where we want to be able to have to make sure that in all situations frequency will not be below 49 hertz. So we do that based on an N-1 situation because we want to avoid load shedding, and that often will happen at 48.8. And then, of course, I should mention that we have actually never been in a situation like this. So, but we still want to avoid that, and also in the future. So you can say that the challenge here is actually not so much the Rokov, but it is more to say handle all the frequency deviations and the challenges that gives us. So next slide, please. So if we then look at the solutions, so what can we do about these low inertia situations? What has been done historically, because it has been quite seldom that we have had inertia situation, could be to reduce imports on our HVDC connections, but that is restricted according to EU electricity market rules. We could also have a must run on thermal power plants and nuclear power plants, but that is quite expensive. We can reduce solar wind production, but that is also last resort according to EU system operation guidelines. And then possibility could also be to increase our FCR reserves, but that's quite expensive. So that's what we could do in the short term. But on the longer term, we can or actually have decided to include inertia as a criteria in our grid planning, in our Nordic grid planning. We can also invest in synchronous condensers. So in Denmark, we have invested and built back in 2015 synchronous condensers both in East and West Denmark to have a more stable system. We could also set minimum requirements for the kinetic energy inertia, but that is currently not the case in the European grid codes. And then there is the market solution, where we could implement a fast frequency and serve that has been a choice we have also taken. But then I maybe should mention that actually there is also another thing going on. As I mentioned, the Nordic is one whole LFC block, but actually this will be changed in 2 years' time, where the Nordic will be divided into 11 LFC areas in the Nordic synchronous area, and then each area will then have its own ACE. So that's also something we do to reduce the frequency deviations that we see, and then have a more robust system, less dependent on some of the inertia challenges that we see. So next slide, please. So just a few words on this requirement for fast frequency product to give the control center a tool that can be used. So in 2019, and after public consultation, we in the Nordic TSOs, we decided to implement this fast frequency reserve because we could see it was a quite cost-effective solutions compared to other means. But we did actually also start changing the requirement for delivery of frequency containment reserve, the FCR, and it's not so fast as the fast frequency reserve. And then we have also optimized the operation of the HVDC connections, where there is a possibility for implementing emergency power control in situations with low inertia. And just a few words on the fast frequency reserve. It is a Nordic demand, but we have national markets, so it's bought individually in each country and implemented last year. It has been decided that we will buy the FFR from May to September, so it's only in the summer where we have the challenges, and it will then also be dependent on needs. So on a daily basis, we look at what is the forecast for inertia in the next day, and if there are no challenges, then we don't buy anything. If there is challenges, then we buy the reserve, and it's between 0 to 250 megawatts. Forecast for demand is based on the modeling and the real-time data, and we see then prices between $50 to $250 per megawatt per hour. And of course, there is a pre-qualification and test of suppliers where we see that, for example, different kinds of demand, batteries and hydropower is then participating in this market. And then there is a product definition where you have different possibilities to bid in. There is 3 ways that you can define your product. I'll not go much into details here. So next slide, please. So just to sum up, and that is, first thing is to understand your challenge. What is it actually that you want to do? How is it you want to balance your system? What possibilities do you have to balance? And why is it that you have the challenges? And for that, it's then important to set up this long-term modeling so you can look ahead, collect the historic data and choose the methodology and do the benchmark and validation. Then to balance the system, then choose your balancing approach. How do you want to do it? Is it reactive, proactive? How is your system built up? Where do you have your congestions in the system? And then have the real-time monitoring to support the control center, but also make sure then that they have some solutions, they have some tools that they can use when they then see the challenges. And here it's important then to set up some criteria for the solution. Is it short-term, long-term? Is it the price? Is it the level of security of supply that is important? Then identify and evaluate these solutions and do it with the public consultations, because often the solutions involve the market participants or the system participants. And then finally, of course, implement and probably often more of these solutions. And then continuously evaluate and improve the setup you have. And we also look into challenges and would like to improve our modeling, especially by including wind and solar, and also including demand in our modeling. But that is quite difficult, but it is something we need to do. We are actually already now including offshore wind, because it is quite large entities that can be controlled, and you have the data necessary to have it in your modeling. So these are some of the things we are looking at right now, and so it is a continuous process that we are working on. So I think these were the words from my side, and I think there is just one large slide. Yeah. So thank you for your attention, and just a few extra links with some information on how Inertia have been looked at in the Nordic system, and also, for example, sharing reserves through HVDC links. That is something that is evolving with increasing use of HVDC links all over the world. So, thank you.
Terrific. Thank you very much, Peter, for wrapping up the presentation portion of our webinar this evening or this morning. For you, especially Peter, thank you very much. I know it is a very, very early hour for you. I hope you've had plenty of coffee, and thanks for giving that presentation. So with that, we have just about 20 minutes left in our session, and I would like to invite all of the speakers to turn their cameras on, and we'll have a little bit of a Q&A session. If you have more questions that have come up during these, after you've seen all the presentations, please feel free to submit them to the Q&A chat option, to the all panelists option. You also do have the opportunity to raise your hand if there is something that you want to engage directly with the speakers, if there's some back and forth that might occur. But you will have to raise your hand for that option, and Isabel will keep an eye out for that. Just before I hop into the Q&A session, just in case we go long, I do want to thank two people who were critical in making this webinar happen. So Isabel McCain helped to actually put all of this together, sent out all of the communications, put the presentation together, and has been doing all of the logistics for us. So thank you very much, Isabel. And then Rob Hardison was also very key in getting all the speakers together. So thank you very much, Rob, for doing that all. Okay, with that, I do want to start jumping into some questions here. So the first one is to all speakers, so feel free to answer this if you feel like you have something you'd like to say. And I think a few of the different presentations did touch on this. But the question is there a possibility to include the inertia requirement in the operation planning, such as like the day-ahead operational planning or day-ahead market? And then is there any suggestions on best practices for combining generation optimization and scheduling with this inertia requirement? Is this something that should be done through reserve requirements, or is this something that is best done as some kind of constraint that would just commit new units, as maybe two different examples that we could do? If anyone has any thoughts on that, please feel free to jump in.
If I could give one input here, from our view, it certainly can be done, and we have then, as I established this separate service or product called the fast frequency reserve, and then have this daily forecast, and then it's published on our homepage what our need is for the next day, and then from the qualified providers, they can then give their bids for the price, and we can then buy it. But you might not necessarily need to have a market like this, but you would say at least the way we do the forecasts that can be implemented. Of course, there's a lot of uncertainties in the way we do our forecast because we only look at the large generators. This was also mentioned by Parag Mitra in his presentation. There are some issues here that it is difficult to do an exact modeling, so or exact forecast. But we try to through a lot of validation of our forecast to take that into consideration, and then based on history and the experience we get now, we must then continuously improve what we're doing. As you saw on this example that I showed from the 13th of June, we did not hit it correctly with our activation of the fast frequency reserve, but we are trying to improve.
Great. Thank you for that.
Maybe I should just one thing. Maybe I should need to mention is that actually there are some differences between the 4 TSOs in the Nordic. Where, for example, Norway they have chosen to buy a continuous reserve because they have not been able to implement in their system to buy it on a daily basis. Because they needed a new, they actually have implemented now a new SCADA EMS system. So of course you need to have the right tool to do this. So
yeah, thank you for the clarifying point, Mr. Huey. You mentioned in one of the responses that you would commit additional generators in the instance that you saw the online inertia drop below the critical level. Is this something that you would consider doing as part of the optimization of the scheduling, or is this more a situational awareness metric that you want to use in the control room and make changes to what is online based on that reliability criteria of monitoring the inertia?
Yeah, well, the turning off of the small hydros that I have mentioned to resolve the problems of when the inertia coming down to the minimum inertia. That one we have applied it in our last holiday when the inertia coming right nearby to the minimum. So it doesn't cross the minimum yet. When it is nearby, then we already have some mitigation solutions, like to start up the small hydros and to keep our conventional power plants without going down to have the renewables coming in. So so that is only our solution for real time right now. We don't have the that in the planning yet, but of course, I think for the near future, we are also looking towards the that process will be taking in the planning. Of course, to have that in the planning, we have to make sure that the monitoring of inertia is correct, so that we can have a good forecast. And from that good forecast, then you can have the inertia requirement in the planning, and you can schedule generators based on that.
Great, thank you. My next question has to do with connections with neighbors. Mr. Huey, I know that you answered a question in the chat about not having appropriate data for your neighboring systems to be able to incorporate into that calculation. So a specific question to you, but also a broader question to the rest of the group on how to think about incorporating neighboring systems' ability to help provide frequency support during some of these times. So the other panelists, you can think about that. But Mr. Huey, I'm wondering if have you had any times where you think that there is critical frequency support or inertia being provided from your neighbors, and do you think that you're missing something by not having that as part of the calculation, or is the connection so small that it doesn't matter? You're currently muted.
Sure. Yeah. So for our case, currently we have the connection with Cambodia, which is our neighboring country. So the link is just based on 220 kV lines, and the amount of transfer is limited. So actually, we don't expect that we will have additional inertia coming from neighboring countries. But of course, by nature, it is there. You know, when you have the interconnection of systems, then the inertia will be coming from both sides. But for online calculation, now we don't have the available data from Cambodia, so we cannot have that in our estimation. Going forward, I think that to estimate that, we will have to have better methods of doing this estimation. I think some more modern methods like parameter I have said, like the regional inertia monitoring, or the more modern method of intrusive power from reactive technologies may resolve that. But for now, we are thinking of that. We are looking towards that.
Great.
Yeah.
Thank you for that. So kind of given building on that, there was Peter, you mentioned there's a question about splitting of the Nordic areas into multiple AGC control areas. So I'm going to ask that question kind of in relation to how neighbors interact with each other. So the question is, you mentioned splitting the Nordic area into multiple AGC control areas, and the question is, what is the reason for this, or what is the reason here?
Yeah, you could say there is actually more. Say one thing is that we have seen historically challenges with the frequency, and one thing has been that when we have then activated, for example, the FCR or the manual frequency reserve, then there have been some congestions in the system, so that we have actually not gotten the reaction that we wanted on the frequency, because the Nordic area was too large to balance as one block. So by then dividing it in more smaller blocks, then it is expected that the frequency should be better. So the reason why we originally had one big block was also because to be able to share reserves from different areas. We will of course still be able to do that, because we will still be having a setup where a market setup where we can share the reserves and have a cost-efficient balancing. So the one reason is that we hope to have a better frequency. The other one is also that with European regulation, where there is being a European balancing market being implemented, there are a lot of new obligations, both on the IT systems and the way that we operate. So then there could be some advantages by doing this now. So the reason why we haven't done it earlier is also that it is involving quite a lot of IT development, both in our control center, but also say in general in the communication with the market participants. So that's the two main reasons why we are doing this. Because it should be mentioned that the reason for the frequency challenge is not necessarily because of increasing share of renewables. It is actually both a consequence of more HVDC links, but also that we see increasing trade between the countries, both in the Nordic, but also with the continent. So also in our modeling and monitoring of inertia, we're also looking at how to better do monitoring of the HVDC lines and how they impact on the inertia. So, and also try to use them more actively, because with the new VSC technology, it is possible to actually to use them very actively in stabilizing the system. So that's something we are learning.
Yeah. Great. Well, that's a great segue into the next question that I have. So it has to do with inverters and the ability for inverter-based resources to provide some amount of frequency support. So the question is, with the knowledge that inverters can provide fast frequency response, if curtailed lower than full output, what is the best way to value the inertia provision, or the frequency support, or the synthetic inertia, whichever term you prefer. And will fast frequency response from inverter-based resources be enough as we move towards higher penetrations? So I open that to anyone who has any thoughts on inverter-based resources providing fast frequency response and frequency support.
Yeah, Josh, I can comment on that a little bit. So yeah, definitely. So fast frequency response and synthetic inertia from these inverter-based resources, they have the capability to stabilize the voltage very quickly. And if you think about synthetic inertia, right, especially the first ones that came out, the wind inertia, what happens in that case is you can actually, if your wind unit is already operating at its peak speed and you do not have headroom, the technology that G had, what you can do is you can borrow some of the energy from the rotating wind turbines. Essentially, you tend to slow down the wind turbine, extract some of the energy, give it back to the system, and then at a later time you have to still retract it back from the system so that you prevent your wind turbine from stalling. The bottom line is that these technologies, they do have the ability to provide very fast support in a very short period of time, typically through derivative controls which respond proportional to the rate of change of frequency change. But when we think about frequency response, right, we have to think about the entire time frame. So if you have something like a battery, of course, it's very reliable, but it's not an infinite source of energy, right? So the battery kicks in very quickly. We've seen this in Australian context, kicks in very quickly. But then as the energy goes out, you still need some of these other frequency responsive units in your system, like coal, gas, or your hydro units to slowly pitch in and pick up from where these battery-based resources or these fast frequency results have gone with. So bottom line being that, yes, they do provide support, and it's something to consider when you think about inertia, minimum inertia requirements. And these capabilities, they will definitely provide more flexibility and more opportunity in terms of how we can schedule our inverter-based resources.
Great. So I'm wondering from the system operators in the room or on the screen, what barriers do you see in terms of being able to rely on these inverter-based resources to provide some of that fast frequency response that Parag was talking about, knowing that there's some additional challenges in thinking about how much they can actually deal with the full extent of the event, the full extent of the contingency event. So I don't know, maybe I'll first kick this over to Mr. Echo, if you have any thoughts on providing a fast frequency response in your system from renewable resources or inverter-based resources, if that's something that you all at PLN would feel comfortable with at this point, or what barriers there might be to incorporating their contribution.
Okay, thank you, Josh. In our system in PLN, especially in Jawa Bali system, the fast response right now is from the gas turbine. And we have around 2,500 maybe. This is maybe is not enough if we will going to the bigger penetration in our system, and we need maybe let's say like a synchronous condenser in our system to get more inertia. Okay, this is our comment, Mr. Rios.
Thank you. Mr. Huey, any thoughts in Vietnam? I know you mentioned wanting to better understand this as part of your inertia monitoring tool of understanding what the contribution could be from those resources. What other barriers might exist to actually incorporating that, and then also using that capability to respond to events?
Well, for fast frequency response of the unconventional source like wind, hydro, and battery storage, we are now pursuing the ability of wind turbines that they can have some kind of synthetic inertia or emulated inertia that can provide extra megawatts in terms of fast frequency response to the low frequency. So, but of course, that is not in our grid code yet. But we are researching on that requirement, and then we hope that it will be soon be available in the both terms of turbines itself, the wind turbines itself, and also in our grid code, so that we can have that function in the future. But for now, we don't have that yet in the grid code, and mostly the renewables are only responding in the time of high frequency, not for low frequency.
Great. Well, thank you so much for that comment. We are at time. I'll maybe allow, if anyone has any final comments about their experience or wants to touch on any of the questions or comments from the other panelists, I'll give that opportunity right now. Okay. Well, terrific. Well, thank you everyone for your participation. We did not get to all of the questions that came through. We have documented those questions, and we'll be sending them out to the panelists to respond, and we'll make sure that we share that information with all of the attendees tonight and this morning. So thank you all again for your participation. Once again, we will be posting the recording of this on the G-PST website within the next few days. So you'll have the opportunity to see this again, and please share it with those of your colleagues that were unable to attend today. I want to thank one last time our panelists. It was a terrific session. I think a great way to kick off this community of practice in Southeast Asia, and looking forward to the next session. Thank you, everyone.
Thanks, everybody. Bye-bye.
Thank you, everybody.
you.
Bye-bye. Josh,
Yeah.
helpful.
Sudah
selesai. Yes. Thank you.
Yep. Bye.
Thank you, everyone. Bye.